All right, hi everyone. So last set of notes on inverse functions. So today we are going to learn how to find the inverse of a function, how to verify the inverse of a function, how to check the inverse of a function, and then how to graph and identify the domain and the range of inverse functions. So today is all about inverse functions. Now, what are inverse functions? Well, to understand inverse functions, you first need to understand what a one-to-one function is. So we all have gone over multiple times what a function in general is. So remember, in order for a relation to be identified as a function, every input needs to have exactly one output. So it goes, you don't have to copy this down, but it goes back into like those algebra 1 skills that, like, if I give you the relation 1, 2, 3, and 4, these are my x's, and then I give you the relation, I don't know, 5, 6, and 7. And if I tell you that 1 maps to 5, 2 maps to 7, 3 maps to 6, and then 4 maps to 5, that right there is a function, because every input has exactly one output, right? This goes to there, and then this goes to there. So every input has exactly one output. None of my inputs have like two separate outputs. It's not, for example, this wouldn't be a function if 1 also mapped to like 6. That's no longer a function because every input does not have exactly one output. So this is a function. But this is not a one-to-one function, because in order to be a one-to-one function, every output has to have exactly one input. So those words there kind of switch. Now, again, this is a function, but it's not one-to-one, because which output here does not have exactly one input? Well, 5. 5 can either map back to x to 1 or through 4. So this is not one-to-one. Now, if I just completely got rid of the 4, right, and had it like this, then now this is a one-to-one function. Every output has exactly one input. Okay, so that's first things first. So in this class, we've been working with functions a lot, but in order to find, whenever I talk about inverses, you need to understand that not only is this a function, but it's a one-to-one function. So one-to-one functions, again, they mean that every output has exactly one input. Now, every one-to-one function has an inverse. No, so every function doesn't have an inverse, but every one-to-one function will have an inverse. Now, what is the inverse? The inverse function is going to be the set of ordered pairs obtained by interchanging the domain and the range of a one-to-one function. Now, that sounds like a lot, but essentially, if this was my function, right, which is one-to-one, because every output, every y, has exactly one x, the inverse, so if I call this one f of x, if I call this this function f of x, the inverse, which we denote through a little like -1 exponent, but we do not say f to the -1 exponent, we just say f inverse, is going, I don't know why I can't close that parenthesis. Let's rewrite this over here. The inverse, so if that's the regular function, the inverse is going to be defined to be where your x's and your y's flip. So your y's become your x's and your x's become your y's. So the 1, 2, and 3 under the x are going to go over here. And then the 5, 6, and 7 under the y are going to go over here. And then you map them out. So the 5 will still go to the 1. The 6 will go to the 3. And then the 7 will go to the 2. So that's its inverse. It's when you swap the x's and the y's. But again, you can only do this if it's a one-to-one function. So for today's set of notes, and the one-to-one function, and just in general, we use inverses a lot within one-to-one functions. There's a lot of special relationships that we know. We know that when we take the composition of a function and its inverse, it always simplifies down to just x. We know that when we graph a function and its inverse, they are symmetric. The two graphs are symmetric with respect to the line y equals x, and a couple of other things. So we're going to go through that today. So I am going to tell you, I'm going to define this function f of x, which is going to be equal to 2x plus 1 over x minus 1. And I'm going to tell you right now that it's a one-to-one function. So because it's a one-to-one function, we are going to find the inverse of it. We are going to check our inverses. We're going to state the domain and range of the function and its inverse, and then we're also going to graph it, okay? Now, in this function, we know that x cannot equal 1, and remember that comes from our domain. Here, if I substitute in a positive 1 there, my function will no longer be defined. So that is given to us from the start, right? The domain is x such that x cannot equal positive 1. So first things first, let's find the inverse of this. And again, we can do that because we know it's a one-to-one function. I'm telling you that it's one-to-one. So in order to find the inverse, what you're first going to do, there's a couple of steps. You're first going to change the f of x notation to old school y notation. So I'm just going to change this to y is equal to 2x plus 1 over x minus 1. So all I did was I replaced this f of x with y. Okay, once you have done that, to find the inverse, you are going to interchange. You're going to swap your x and your y variables. So wherever you see an x, you're going to change it to a y. Wherever you see a y, you're going to change it to an x. So this will look like this. That first y is going to change to an x equal to 2. That x is going to change to a y. And then that'll be a plus 1. Over that y, that x is going to turn to a y minus 1. Okay, so all I did right there was I interchanged, I swapped my x's and my y's. Now what you're going to do is you're going to solve your new equation for y. To do that, because it is a rational equation, we have to first get rid of that denominator. So let's go ahead and multiply y minus 1 to both sides. Since it is a binomial, you should write it in parentheses. These eliminate out, and then you're left with just 2y plus 1 equals, right here you can go ahead and distribute out that x, so that would be xy minus x. And then again, your goal here is to solve for y, solve for y. So let's get our y's to one side and then our x's to the other side. So here I can subtract 2y to this side. And then I can add x to this side. So this eliminates out, xy plus minus 2y, those are not like terms, so I'm just going to bring them down separately. And then equal to 1 plus x are not like terms again, so I'm just going to bring those down separately. Again, my goal here is to solve for y. I see that on the left-hand side, both of those terms have a y that I can factor out. So I'm going to factor out that y, and I'll be left with just x minus 2 equal to x plus 1. And then lastly here, to solve for y is you're going to divide both sides by x minus 2. This eliminates out, and then you're left with y is equal to x plus 1 over x minus 2. This equation is now solved for y. So once you do that, you're going to change it back into function notation by changing that y to f inverse of x. Remember, we went over that earlier. It's not to the negative 1 power. That's the notation for inverse, is equal to x plus 1 over x minus 2. All right, so algebraically, that is how you solve for the inverse of a one-to-one function. Again, quick recap. You first change from function notation, you change it to just a y, and then you swap your x's and your y's, and then in your resulting equation, you solve for y. Once you solve for y, you go back into function notation. All right, so that's step 1. That's the first thing that'll be asked of you on your classwork. Find the inverse. Once you have found the inverse of a function, you need to check that they are indeed inverses. Now, to check, it is a little bit of work, so make sure you are ready for this. The way that you check that a function and its inverse are indeed inverses is you have to take the composition of functions, which we learned in the last lesson. So you know that two functions are inverses of one another if when you take the composition of f inverse and then f inverse of f, you result in your resulting composite functions are just x. So if I take f composed with f inverse of x, I should end up with just x. And then we'll need to do the same for f inverse composed with f of x. Now again, this will, especially because our functions have fractions in them, it's going to get very algebra heavy. We're going to have to do a lot of triangle method, a lot of in and out, a lot of just basic algebra skills. So if you get stuck at any process in this, make sure that you ask me during class time. Honestly, for time purposes, I might not show both of them to you. I will probably just show one, but you should ideally still practice the other one to verify that you simplify down to just x. So I will go ahead and do the top one, and then like I said, you should do the other one by yourself because it will be a little algebra heavy. So what does this mean? Going back to what we know about composition of functions, this is telling me to substitute in the inverse function into f. So let me go back up to what f is. F was 2x plus 1 over x minus 1. So it's 2x plus 1 all over x minus 1, right? But I am not substituting in x. I am substituting in the inverse that I just solved for, which is this. So for x, I am going to substitute in x plus 1 over x minus 2, x plus 1 over x minus 2. Look, just by looking at this is a very involved fraction. So like I said, it's going to be a lot of simplifying here. To simplify this down first, I would first distribute out this 2 to this fraction. Remember, this is like 2 over 1. When you multiply fractions, you only do numerator with numerator, denominator with denominator. So this will simplify down to 2x plus 2 all over x minus 2. And then I just carry over my plus 1 all over here. There's not much simplifying I can do, so this would just be x plus 1 over x minus 2 minus 1. Then these are two terms that either need to be added or subtracted, two fractions. So you got to get a common denominator. I will be using my triangle method to get my common denominator. So you're going to multiply 2x plus 2 times 1 first, which just gives you 2x plus 2. You're going to multiply 1 times x minus 2, which is just going to give you plus x minus 2, over, then you multiply across, which just gives you x minus 2, all over. Again, you do x plus 1 times 1, which is just x plus 1, minus, then you do 1 times x minus 2 here. Be careful because you have this minus sign here. This is like a minus 1 times x minus 2. Whenever it's subtraction, you do need to be careful with your parentheses because that negative needs to be distributed all over x minus 2. Here you do more simplifying. You combine some like terms. 2x can be combined with that. This can be combined with this. And then here, make sure that you distribute out that negative. So 2x plus x gives you 3x, plus 2 minus 2, those eliminate, all over x minus 2, divided by, here this would be x plus 1, distribute out that negative, you get negative x plus 2, all divided by x minus 2. Again, do some simplifying down here. X can be combined with negative x, and then positive 1 can be defined with positive 2. So this would give you 3x over x minus 2 all over x minus x. Those simplify out. 1 plus 2 is 3 over x minus 2. Complex fraction. We're getting close. Remember, our goal here, if these are indeed inverses, it should simplify down to just x. So 3x times x minus 2, let's not multiply that out. Let's just write them side by side. Over, let's do our inners. So that would be 3 times x minus 2. Here, ta-da, a lot of stuff is going to eliminate. Your x minus 2 eliminates, your 3 eliminates. So all of this simplifies down to just x. So again, you need to know how to verify inverses, and this is how you do it. If an inverse and its function are indeed inverses, once you take the composition of them, all of the algebra should simplify down to just x. Now, you do have to do it both ways. Right now, I substituted the inverse into the original. You also now need to go the other way around and substitute in the original into the inverse, and that should also give you x. This is what I'm telling you I'm not going to do for time purposes, so you should try it yourself. I will check it in your notebooks at some point. And if you don't get x, you need to practice these algebra skills, okay? So come to tutoring or let me know, ask me questions, watch YouTube videos, whatever. Okay, so that's the next part. Again, I'm going through all these steps because your homework is going to ask you to do this. The first part of it is to find the inverse. We found it. Then you're expected to check your inverses. How do you check? You take the composition. Next thing that you have to do is you have to state the domain and the range of your function and its inverse. So let's first state the domain and the range of f of x, and then let's write in blue, of f of x. And then we will also find the domain and the range of the inverse, f inverse of x. Okay, so let's start with the original function. So what was the domain of our original function? Well, in this original function, remember, it was given to us. X could be anything you wanted but +1, because if you substitute in +1, you get 0. So the domain of f of x is x such that x cannot equal +1. Now, remember, because what I told you from the start, this was a one-to-one function. If you go back to what I did over here, think about what's happening here. What's the relationship between a function and its inverse? Well, all of the x's interchange to become y's. And all of the y's swap and become x's in the inverse. So if I tell you that the domain of f of x is x such that x cannot equal 1, then the range of the inverse is x, sorry, not x though. Ooh, see, I almost got automatic mode. Remember, range is with respect to y, so it's going to be y such that y cannot equal 1. Okay, so remember, an inverse and its function, the relationship is that the x's of the original function turn into the y's of the inverse, and then the y's of the original function turn into the x's of the inverse. So here, once you find the domain of f of x, you automatically now know the range of f inverse of x. Now, if you're thinking, okay, how do I find the range of f of x? Well, the range of f of x is the same thing as the domain of f inverse of x. And we know what f inverse of x is. We solve for it right here. So now let's define the domain of f inverse of x. Well, the domain of f inverse of x is x such that x cannot equal +2. Because if I substitute in +2 into this function right here, I'm going to get 0 in my denominator. So my domain of my inverse is x such that x cannot equal +2. And like I said, the domain of because they interswap, if it's the x's on the inverse, then it has to be the y's or the range on the original function. So it's y such that y cannot equal 2. Okay? Take a second and process that. Let me know right off to the side if you have any questions. Okay, there's one more part to this inverse notes. So the last part is you need to see, I want you all to see the relationship of a function and its inverse on a graph. So the fourth part of the homework is going to ask you to graph the two functions with making sure to include the line y equals x and seeing that they are indeed inverses of one another. Now, I am going to be nice and I am not going to make you actually graph by hand. I will have you all graph on Desmos. And as long as you can see that relationship, and then on your homework, just do a quick sketch once you have it. But you can use Desmos to graph it. So let's go ahead and let's see what those graphs look like. So if I go to Desmos and let me type in my original function f of x, which was 2x plus 1 over x minus 1. Okay, there's my original graph. We know that it is a rational equation, so if you remember your parent functions, we should expect it to look like this. Now let me go ahead and graph the inverse that we got. The inverse which we got was x plus 1 over x minus 2. So that's what we see in blue. Now, these two graphs have a very special relationship. Remember, a function and its inverse are the interchanged versions of one another. So, what does that mean? Your x's become your y's, and your y's become your x's within a function and its inverse. So here, these are actually symmetric with respect to the line y equals x. And why is that? Well, because that's the definition of an inverse. The definition of an inverse tells you that your y's become equal to your x's, and your x's become equal to your y's. Now, what is y equals x? Well, remember, if you think back to our parent functions, y equals x is the parent function of a line. In this line right here, it's the most basic version of a line where my slope is 1 and my y-intercept is 0. But I don't ever write that that 1 and that 0, right? But essentially that's what's happening here. My y-intercept is 0, and then for my slope, I'm going up 1 unit over 1 unit, up 1 unit over 1 unit. It is the most basic version of the line. It's the line y equals x. And that's just something that you all need to know. You all need to understand that a function and its inverse, when you graph them, they are symmetric with respect to the line y equals x, because again, that's by definition what an inverse is. Your y's become equal to your x's, and your x's will become equal to your y's. They swap one another, and they're symmetric, right? Remember, we've talked about different types of symmetry. There's symmetry with respect to the x-axis, to the y-axis. These are symmetric with respect to that green line that we see on the graph. Like if I were to fold the two graphs over that line, the blue part would match up with the red part, and then the vice versa, right? And that's again because inverses, a function and its inverse are the interchanged version of one another. All right, so on your homework, once you have a function and its inverse, go to Desmos, graph them, make sure you also include that third line of y equals x, and verify that they are indeed symmetric with respect to the line y equals x. So again, main point here you need to realize are inverses are symmetric with respect to the line y equals x. All right, so as long as you have verified that through Desmos, including that y equals x symmetry line, then you are good. All right, these are the notes on inverses. If you read the directions on the notes, it's going to ask you to do these exact things. They're going to tell you a one-to-one function. You're going to need to find the inverse. You're going to need to verify the inverses. And yes, you verify it both ways. I only did one way. You will do both. I only gave you 2 questions, though. You're going to state the domain and the range of the inverse and its of the function and its inverse. And then you will verify that the graphs are indeed inverses, and you'll know because you'll notice that they'll be symmetric with respect to the line y equals x. All right, let me know if you have any questions.